The first speaker of this session will be Andy Hardt from University of Minnesota, and he will be talking about lattice models and Hamiltonian operators.
Okay, thanks, Suji. Thanks to the organizers. So I'm going to talk today mostly about lattice models, a little bit about Hamiltonian operators, and also about sort of a correspondence between them. So first of all, before we really get into it, I want to show you this diagram. So I'm biased, and so I put lattice models right at the center here. But the point is that they have a lot of connections with a lot of really interesting fields of mathematics that aren't even really restricted to combinatorics or algebra or anything. So they come from statistical mechanics. They actually are the origination of quantum groups. We're going to see some stuff about symmetric functions. They relate to Schubert calculus. They relate to conformal field theory. They relate to p-adic representation theory and to probability and to other areas that I didn't mention here. And so we're going to sort of, at least a little bit, kind of just brush up against these circles in blue, and we're really going to leave the rest of them alone for now. But there are tons and tons of relationships between lattice models and other things. So if there's one thing you take away from this talk, I hope it's that lattice models are cool. So what are they? I've built them up. Basically, they look like this. There are these rectangular grids of vertices. There are other kinds of lattice models that don't look like this, but we're going to focus here. So you can see here we have each vertex is where two lines cross. And these circles kind of don't exist. They're just a place for us to put a spin. So each edge here between two vertices, each edge has a spin. And in this case, we can fill it in as either a plus spin or a minus spin. And in other contexts, there can be other decorations too. And so if you look at a given vertex, you can look at the four spins around it, and it would create a vertex like this. And so we have here a minus, a plus, a minus plus going from the top clockwise. And so we call a vertex admissible if it is one of several allowable configurations. And the set of allowable configurations depends on our lattice model. So this is, in general, these can be from any sort of table that we come up with. And if something is an admissible vertex, we give it a weight called a Boltzmann weight. And you will notice that if I fill in, say, a bunch of spins here, then if I kept going through the whole thing, the spins on next to one vertex are also next to a different vertex. And so each vertex affects its neighbors. And so this is local behavior affecting the global behavior of the system. And so if you're able to assign spins such that every vertex is admissible, we call this an admissible state. And the weight of the state is the product of the weights of the vertices. Okay, so how do we come up with special functions with these objects? Well, there are many ways, but one of the most important is called the partition function. So we fix the boundary spins like I've done here. And then the interior spins, if I just delete these, we can sum over all possibilities of these interior spins such that we get admissible states. And so if we sum the Boltzmann weights of all of these states, we get a function that we call the partition function. So I've called this Z right here. Okay, so this is a way for us to construct functions. And right now there's nothing special about it because you could make any combinatorial system and create functions that come from this thing. So I'm going to illustrate some of the nice properties by an example. So this example is the 6 vertex model. It's maybe the most famous lattice model. And so the 6 admissible vertices, our table of them is right here. So we have A1, which is all plus, A2 all minus, and then B1, B2, C1, and C2. And one of the reasons this is really important is because this comes from physics. So if we think of a sheet of ice, each oxygen atom is connected to 2 hydrogen atoms, it's H2O. But in reality, we have, say, a grid, say a 2-dimensional sheet of ice. The oxygen atoms are next to other oxygen atoms. So in this framework, the vertices are oxygen atoms, the edges are horizontal atoms, and the spins represent the fact that the horizontal edge is the hydrogen is in between 2 oxygens. And so it's either going to be associated, meaning close to one oxygen or the other oxygen. So it's not, it's a little bit involved to say what plus and minus mean in this context, but essentially they're telling you which oxygen atom the hydrogen atom is near. And so the 6 vertices, if you think of it this way, end up being the 6 vertices where every atom is an H2O atom. In that context, the Boltzmann weights correspond to the energy at that vertex. And so the partition function is in some sense the energy of the system, or related to the entropy of the system and the probability of certain states arising. We're not going to do that here. We're going to create different Boltzmann weights that don't correspond to this. And so we're going to see other functions that are more important in pure mathematics. So here are our Boltzmann weights. And so if you see an A1, you just multiply by 1. That's easy. Same with B1, same with C2. Now, if we see a B2, I want to multiply by a ZJ. Now, what's ZJ? Essentially, it's a row parameter. So we are introducing, for every row of our lattice model, some row parameter, okay? And so that means that if I see a B2 vertex, and it's in the first row, so it's plus, minus, plus, minus. So say I make it here. This is going to get a weight of Z1. Okay, if I saw it in the second row, it would get a Z2 and so on. Okay, I'm just defining these things. So what? Okay, so suppose then okay, so we have our Boltzmann weights. We want to get a partition function, so we also need boundary conditions. So I've written these boundary spins down in a very particular way. I put pluses on the left, pluses on the bottom, minuses on the right, and on the top, we have a mix of minuses and pluses that corresponds to this partition lambda. We've shifted lambda so that it's strict. But the parts of lambda plus rho are 4, 3, and 1. And in this way, as long as we can take more columns if we need to, we can put every partition, give it its own lattice model. And then we can compute the partition function of this lattice model. I'm telling you that the partition function here is interesting. So what is the partition function? It's what's called the Whitaker function. So the Whitaker function is a function that comes from p-adic representation theory. It's associated to Whitaker models. And if I compute the partition function of this, it ends up being the Whitaker function evaluated at this torus element corresponding to lambda and with a character that's given by the row parameters. Now, you guys are combinatorialists, so I think more to what you'll be interested in, if we specialize the TJs to 0, then this becomes just the Schur polynomial. And so we found yet another way to represent Schur polynomials combinatorially. Okay, and so when we have Schur polynomials, I want to ask, does our combinatorial structure reflect the properties of the Schur function? If not, it's not a very useful thing. And so most importantly, we're getting symmetric functions. So why do we get symmetry here? Why do we get a Schur function, or the Whitaker function has a sort of symmetry to it? Why do we get symmetry? The answer is the Yang-Baxter equation. The Yang-Baxter equation, aka solvability, is this equation. Okay, so what do I mean by this equation? What I mean is we already have admissible vertices and Boltzmann weights for these rectangular vertices that appear here. And I will allow you to choose whatever Boltzmann weights you want for these diagonal vertices. If you can do it in a way such that regardless of the boundary conditions I choose, these two partition functions are equal, we will call that a solution to the Yang-Baxter equation. So it's a choice of this other sort of weights that makes partition functions equal. Not clear at all why we want this right now. I'll tell you in a second. These really, the main source of solutions to the Yang-Baxter equation are quantum groups. That's just why quantum groups were even developed. So that's a whole other area that's very, very interesting, but we're not going to talk about. Okay, so I promise we're going to talk about symmetry. Why does the Yang-Baxter equation give us symmetry? It's because when we have this solvability, we can do the train argument, which means I have a lattice model. It has 2 rows, but it could have more. It has 2 columns, but it could have more of those as well. But I've attached to the left of it this diagonal vertex. And if I apply the Yang-Baxter equation, I can push this vertex into the middle. And if I push it again, apply it again, I can push it over to the right. And what have I done here? What I've done actually is I've swapped the row parameters. You'll notice that we have a Z1 on the top, a Z2 on the bottom, but when this goes to the diagonal vertex, it moves down. And that's not part of our rectangular piece, so we don't really care about it. But once I pushed it through, the Z1 now is the bottom of the lattice model. And so if we can pop these vertices off, then this tells us a functional equation of the partition function of the model. And in the case of Schur polynomials, it's particularly simple. We just get that this partition function equals this swapped partition function. And so the upshot is that if I switch to parameters of the Schur function, I get the same thing. And so this is a way to prove that Schur polynomials are symmetric. We can also use lattice models to prove other identities, such as Cauchy identities or branching rules. I'm not going to really get into those except to say that we really care about identities we can prove through these combinatorial constructions. And so this is going to lead us into our next piece, which is Fock spaces. And Fock spaces are somewhat similar to lattice models on first glance, and they're somewhat similar on a deeper glance, but those are sort of different perspectives that we have to take. So this is also from statistical mechanics, and it also gives similar identities like Cauchy rules, branching rules, Peary rules, Jacobi-Trudy rules. And so if we want to play with a correspondence, we can go back and forth and prove our identities on whatever side we want. So the goal is to find a correspondence between these two constructions. So what is Fock space? There are representation theoretic versions of this, but I'm just going to talk about it schematically. So Fock space, a state of it is you have particles to the left, holes to the right, and in the middle we have some particles that have jumped the fence and alighted on positions 1, 3, and 4. And so this corresponds to the same partition we talked about. Lambda plus rho is 4, 3, 1. And so immediately we have some similarity on like the most superficial level, that these correspond to partitions. And we also have certain operators, current operators coming from a Heisenberg algebra, that basically move a particle to the left. So if we apply J1, it's going to move a particle 1 step to the left, or 1 step to the left. If we apply J2, it moves it 2 steps to the left, or 2 steps to the left. We also have an exclusion principle. If you want to move this 2 steps to the left, you've got to move this one out of the way first. And our question, one question we can ask is, what combinations of the current operators gives us this vacuum state where all the particles are safely in the ground state? And in order to do this, I'll tell you something that really doesn't work, which is, say I had this state here, 4, 3, 1, and I applied J1 to it. That's a single current operator. And I paired it with a vacuum state. So this is sort of how can we do this state, apply J1, pair it with the vacuum state. Does this work? What's the weight of it if it does work? And the answer is it obviously doesn't, because I can't get all 3 of these particles over here just by applying one copy of J1. There's no way I can do that. On the other hand, if I apply just a J1 to here, I could get from 4, 3, 1 to say 4, 2, 1 by going down. This 3 goes down 1 spot to a 2. Okay, so by applying successive current operators, we could make our way to the ground state. And this Braquet notation, which comes from physics, kind of tells us the contributions with each current operator moving between the states. This also looks like what we could see in lattice models. So see here, we have a particle at 4, a minus sign, and it just stays at 4. The particle at 1 just stays at 1, and the particle at 3 moves over to 2. So again, combinatorially, these things are obviously very related. Algebraically, it's a tougher story. So what we do in order to apply many current operators is we define this Hamiltonian operator. It's this weighted sum of the current operators. These parameters are going to be similar to our Boltzmann weights. And we take a formal exponential that allows us to apply the current operators as many times as we want. And I know I'm running out of time, so I'll just briefly summarize some of the correspondences. So the question is, when does the partition function equal this bracket for the Hamiltonian? And when does this happen for all lambda? So can we find sets of Boltzmann weights for the lattice model and sets of parameters for the Hamiltonian such that these quantities are equal regardless of our partition? And the answer is yes, we can do this, although not in all cases. So this is from Zen-Justin's notes. It might predate him, but if we do the sure polynomial weights we had earlier, and we set these parameters to the power sum symmetric functions, we get equality. Brubaker and Schultz showed that if we use weights, the Whitaker function weights that we saw earlier, and then instead of power sums, we get these superalgebra versions of these power sums for our Hamiltonians. And most recently, I've seen that if we, so both of these things, these weights satisfy what's called the free fermion condition. And so if we do satisfy the free fermion condition, regardless of our weights, we can get a Hamiltonian. And I wrote out the specific parameters of the Hamiltonian because I find them interesting. I don't know why, but these expressions relate to sure positivity in some way. And I won't get into potential generalizations, but I'll have that in the notes. So anyone who wants to can look at that afterwards. Thank you very much.
Let's thank our speaker. Does anybody have a question for Andy?
I have a question.
Yeah.
When you had that notation with the pairing of the operator and the two states, that doesn't capture which one you apply the operator to, which particle. Does it not matter? Or
Right. So I didn't write what the current operators are algebraically, but they're essentially a sum over all possible one particle motions. So we could have more sort of atomic things that only can move this particle over. But yeah, so what it would mean is if we have a bunch of different ways to go from this one to this one by moving a single particle over, then instead of this being just one, it would be 5 or something, or it would be there'd be some weight. But that's a really good point.
Thanks.
Thanks, Sasha.
Any other questions? Okay, then I have one. You did say that.
I have a question, sorry.
Okay, Sarah, go ahead.
Well, so you mentioned potential generalizations. So maybe since we have a few minutes, can you show us your notes about them?
Sure, yeah. So this stuff is very much kind of in progress.
Mm-hmm.
But so say we take the 6 vertex model and instead we say, let's take a generalization of this model. So we're not doing the pluses and minuses anymore. So we're generalizing the 6 vertex model to what's kind of a metaplectic analog, which is models with color or charge. They're sort of equivalent. And if you generalize Fock space to the quantum analog Q Fock space, you do get a correspondence. So this is by Brubaker, Busiumis, Bump, and Gustafsson. They showed that on the lattice model side, we'll get certain functions called metaplectic symmetric functions. On the Hamiltonian side, we get this Hamiltonian that comes from a specialization of supersymmetric LLT polynomials. So it turns out, I think it's very interesting that metaplectic and quantum have these relationships because they're not necessarily equivalent generalizations. And so we can go a little bit farther here. I've been stuck to get it too much farther, to be honest, but if we have lattice models with charge satisfying this kind of complicated condition, then it corresponds to Hamiltonians with parameters that look like this. So thanks, Sarah.
Well, thank you.
Let's thank Andy again.